All right, everyone. Today's lesson is one of the most important lessons in all of pre-calculus. I'm going to introduce the unit circle, which is something that we're going to talk about for the rest of the course. So I'm going to start by talking about the unit circle. I'm going to give you new definitions for sine, cosine, and tangent, and then we're going to derive sine and cosine for special angles on the unit circle. It's okay if these bullet points don't make sense yet. They will by the end of today's lesson. So first of all, your warm-up, fill in the missing side lengths of the two special right triangles below. This will require you to have some knowledge and memory from honors geometry about what special right triangles are. So I would pause the video, try this on your own, because I'm going to go through it in about 5 seconds. So you might remember these special right triangles from your geometry class. This is kind of like the answer key or the reference information. I took this right off the MCAS reference sheet, and it tells you how the sides of these triangles relate to each other. So let's just look at this really quickly. You'll notice in the 45, 45, 90 triangle, the two legs are the same, and then the hypotenuse is x times root 2. So if you know what the leg length is, and you wanted to know what the hypotenuse was, all you have to do is multiply by root 2. To do the opposite, let's say that you knew what the hypotenuse was and you wanted to use that to find the leg, you would be dividing by root 2. And I'm going to talk about that in a minute when I go through this problem. For the 30, 60, 90 triangle, if you knew what y is, if you knew what this shorter leg was, you would multiply by 2 to get the hypotenuse. If you knew the hypotenuse, you would divide by 2 to get this leg. If you knew this leg, you would multiply by root 3 to get the leg opposite the 60-degree angle. And then if you knew this leg and wanted to know the shorter leg, which is the one over here, you would be dividing by root 3. So let's apply that. Let's apply this to these pictures. This is a 45, 45, 90 triangle. I know the hypotenuse. I'm going to divide by root 2 to get both leg lengths. And then I'm going to write my answers with rationalized denominators. So I'm multiplying by root 2 over root 2. And you get final answers root 2 over 2. Over here for this 30, 60, 90, we know the hypotenuse. I'm going to start by finding this leg, the leg opposite the 30. So I'm going from 2y to 1y. I'm dividing by 2, so you get 1/2. If you know the side opposite the 30, you take that and you multiply it by root 3 to get this side opposite the 60. Make sure you have these triangles copied down because they're going to be our cheat sheets later on today. All right, what is a unit circle? It's a circle with its center at the origin and a radius of 1. Here is a picture of the unit circle. All of these coordinates should make sense to you. If the radius of the circle is 1, we can understand why this circle would go through this point 0, 1. So the definition of a unit circle is pretty easy. Here are your new definitions of sine, cosine, and tangent. And you might be wondering why I'm using the word new definitions. That's only because if you took geometry, you already have definitions of sine, cosine, and tangent. You probably learned the acronym SOHCAHTOA. That acronym and those definitions of sine, cosine, and tangent were helpful in geometry, but they were limited definitions. So now that we're older and wiser, we have new, more advanced definitions of what sine, cosine, and tangent are. So let's read this sentence together. Theta is the measure of an angle in standard position, and I'll remind you of what that means in a second. X comma y is the coordinates of the point where the terminal ray intersects the unit circle. What the heck? If this sentence is too much to digest alone, let's draw a picture that goes along with it. So here is an angle in standard position. I randomly drew this angle theta. It happens to be a quadrant 1 angle, but this definition works in any of the quadrants. So look, we've got this random angle, angle theta. This is the terminal ray. which is going to hit our unit circle somewhere. The coordinates of this point are x, comma, y. And then our new definition of the trig functions says that sine of theta, so sine of this angle, whatever it is equal to this y coordinate. Cosine of theta is equal to this x coordinate, and tangent is y over x. All right, so we could write this coordinate as x comma y, or we could write it as cosine of theta comma sine of theta, since this new definition says that those things are equal, right? X is the same as cosine of theta, and y is the same as sine of theta. I think this is a really great visualizer. Let me pull it up just to make sure everyone understands these definitions. Visualizer lets me pick my theta. So like right now, theta is 124 degrees. We can see that this point right here has coordinates negative 0.56 and 0.83. And then we can see that that's what sine is. Sine is just equal to whatever that y coordinate is, and cosine of theta is just equal to whatever that x coordinate is. It's kind of a cool visualizer. It lets us visualize sine and cosine for angles between 0 and 360. That you might have in your mind right now are, why do we have these new definitions of sine, cosine, and tangent? Why can't you just use the SOHCAHTOA definition of sine, cosine, and tangent that you learned in geometry? The reason for that is because the SOHCAHTOA definition that you learned in honors geometry, that only applies to angles in quadrant 1. This new, more advanced pre-calc definition of sine, cosine, and tangent lets us talk about angles that are in the other quadrants. And then we'll talk about on the next slide how these two definitions are related. That's a really important thing that I want you to come away with today understanding. How is your honors geometry SOHCAHTOA definition of trig related to these new, seemingly more confusing definitions of trig? So here's our unit circle. I'm going to talk about sine, cosine, and tangent of these angles a lot. So let's find what sine and cosine of these angles are, and I'll show you how to find them, right? We're going to find them by finding the x and y coordinates of all of these points. All right, let's start with 30. Let's find sine of 30 degrees. The slide is all about 30. And in order to find these x and y coordinates, I'm going to draw a right triangle, right? So this degree is 30. The hypotenuse here is 1, and hopefully you know why that's 1, because if this is a unit circle, that means that the radius is 1. So since this hypotenuse is a radius, it's already labeled 1. Again, we want to find the x and the y coordinate of this point. If we wanted to visualize the x and the y coordinate in this picture, the x coordinate would just be the same as this horizontal distance, and the y coordinate would just be the same as this vertical distance. So I want you to think for a minute, maybe pause the video, and think about how we could find this x and this y. Hey, wait a second, Miss Coffin. We already found x and y. That was your warm-up. Sneaky Miss Coffin, we already have the answers, right? We already found x and y. This is me just copying and pasting the answers that we already got from the warm-up. So we already know that x would be root 3 over 2, and y would be 1/2. So those are the coordinates of this point. I could see myself in a future test or something forgetting that sine was equal to the y coordinate. So let's talk about how your SOHCAHTOA definition of trig also relates to this new definition of trig. So look, if we think about SOHCAHTOA, sine is opposite over hypotenuse. So sine would just be y over 1. All right, so if you ever forget that sine is equal to the y coordinate, you can just sketch a little right triangle and say, all right, if sine is opposite over hypotenuse, sine is just equal to y over 1. All right, so that's how those two definitions relate. But again, our new definition of trig is better because it lets us talk about angles that aren't just in quadrant 1. Let's carry on. I want to fill in these other coordinates for these quadrant 1 angles. So let's start here with 45. Let's draw our little triangle. Again, it has a hypotenuse of 1. Again, if we're looking for this x and y coordinate, this distance is the same as the x coordinate. This distance is the same as the y coordinate. we want to find x and y, and OMG, we've already done that, right? We've already found x and y. Again, we did this in the warm-up. X and y are the same, and they are both root 2 over 2. All right, last one I want to talk about in quadrant 1 is 60 degrees. So again, I'm doing it the same exact way I found the other ones. I'm sketching a right triangle. I'm recognizing that this horizontal distance is the same as the x coordinate, and this vertical distance is the same as the y coordinate. I'm asking myself how I can find x and y. And again, we already did this in the warm-up. Here's a copy and paste of my warm-up answers. And yes, this triangle is oriented differently than this one, but if you kind of tilt your head, you should be able to figure out that this x would be 1/2, and this y would be root 3 over 2. So it's the same coordinates as the coordinates that I had down here for 30 degrees. The x and y have just switched. This should make sense, right? It's the same triangle, it's just a triangle that's oriented differently. Now that we have quadrant 1 filled in, filling in the rest of the quadrants is really easy. So let's start here. Let's say that I wanted to find the coordinates of this point right here for 150 degrees, right? So 150 degrees, what are the coordinates here? We don't have to reinvent the wheel. We can use our answers that we had over here, right? If you think about it, if I wanted to draw a right triangle, it would be a right triangle that has degree 30 here, right? Because 180 minus 150 is 30. So it's the same triangle that we already talked about over here. This point is heavily related to this point. It's a reflection of this point across the y-axis. All right, so we actually already know the coordinates of this point. It's just a reflection of this point, right? The y-coordinate is going to be the same because this point and that point are at the same height. And the x-coordinate is just opposite, right? Because this distance from the point to the y-axis is the same as this distance from the y-axis to this point. So if you already know your quadrant 1 angles, you can just think about reflecting points across the y-axis to get your quadrant 2 angles, right? This one would be negative 1/2, comma root 3 over 2. And this one would be negative root 2 over 2, comma negative root 2 over 2. Again, this should make sense. The x-coordinates have been made negative because this point is a reflection of this point. And then this one should make sense. This is 0, comma 1, since the radius of our unit circle is 1. It's pretty easy to fill in the rest of the unit circle if you just consider reflections. So you might want to pause and try it on your own, or you can just keep watching the video. Both of these coordinates would be negative. I like to think about reflecting this point across the x-axis. All right, so these 2 points have the same x-coordinate, but the y-coordinate at this point is negative, right? So I can fill in the rest of these coordinates. They're both negative, right? It's the same as these coordinates, except the y-coordinate is also negative. This point would be negative 1, comma 0. I can also fill in this quadrant. Again, I'm just probably thinking about taking these points and reflecting them across the x-axis. So the x-coordinate of like this point compared to this point is the same, but the y-coordinate is negative, right? So we can fill that in, right? X-coordinate's the same, y-coordinate's negative. Same deal with all of these points. If we compare them to our quadrant 1 angles, the x-coordinate's the same, but the y-coordinate's negative. All right, so that's a quick description of where these coordinates came from. It's a quick explanation of this new definition of sine, cosine, and tangent. And I'm hoping that you can see how it relates to your geometry definition, where sine is opposite over hypotenuse. We'll continue to practice with this in class. And I just hope that this video helps you understand where these numbers come from, so it doesn't feel like something that you need to memorize. Worst case scenario, you would have to memorize quadrant 1, and then the other quadrants 2, 3, and 4, just make sense because they're reflections of the same coordinates.